right, so the central dogma of biology states that DNA encodes for RNA, which in turn encodes for protein. And we, as human beings and all living things, are essentially just big sacks of protein. So in this way, DNA makes up who we are. Okay? So how do we get from DNA to RNA and RNA to a protein? That's what we're talking about today. Step number 1 is called transcription. All right, so I'll just write that in here. Transcription. All right, so we're literally transcribing are transcribing the DNA into the RNA. All right, so it starts off in a process called initiation. So initiation begins when the DNA is again unwound, and it's going to form, instead of a replication fork like we talked about in DNA replication, it's actually going to form a transcription bubble. All right. And how does it know where to bind to or where to begin? Well, there's a region on the DNA called a promoter. So remember, this is the DNA right here, okay? And this promoter basically says, hey, come over here, you enzymes. In this case, it's going to be RNA polymerase. It's going to come, here's your enzyme here, RNA polymerase. And it says here, bind here. This is where you would like to begin. This is where you need to begin. So it's going to, just like a club promoter, its job is to bring the people to the party, right? To bring the RNA polymerase to the right place to begin transcription. Then we have the process of elongation. So RNA polymerase actually goes in it synthesizes in the 5' to 3' direction, and is essentially going to just pair up the DNA with mRNA nucleotides. Now, here's the trick. We haven't talked about the difference between RNA and DNA, but one that you're going to see here is A goes with U. So in DNA, A always goes with T, right? Because that is Chargaff's rule. But in RNA, there's no thymine. So instead of thymine, RNA has uracil. A. All right. So the rule now for creating RNA is going to be A always goes with U when you're in RNA. Okay. Now the type of RNA we're making is mRNA, and M stands for messenger. Okay. So this is very literally a single strand. So notice this is we're making one single strand of RNA, of mRNA, to get the message of DNA out of the nucleus, because the nucleus, right, it has just tiny little pores in it. Remember, we talked about the nuclear envelope and the nuclear pore, and it has just tiny little holes in it. And because of that, right, because of those holes, DNA is too big to get out. So the only way we're going to get it out is if we substitute a double-stranded something for a single-stranded something. So right here, I want to just stop and summarize the difference between DNA and RNA. All right. So RNA has uracil. RNA is single-stranded. RNA can leave the nucleus. Okay. All right. DNA has thymine. It's double-stranded. And it's stuck in the nucleus. We also need to go back and think about those sugars. Don't forget, this is deoxyribose sugars. And this is a ribose sugar. Okay. Now, there are going to be three kinds of RNA we're going to talk about. We already talked about mRNA, and this is going to take the DNA message out of the nucleus. Now, we also have tRNA and rRNA, and we're not going to talk about those until the next time. So just know that those exist. All right. So that is the difference between DNA and RNA. And you might just want to type this up in your notes somewhere, like at the bottom, or if you have a stylus, you can write by hand, or you can write and take a picture and then copy it in your notes, whatever works best for you. So now, once we've created this long mRNA strand, that's what this guy is right here, this strand right here. This guy is our mRNA, all right? Once we're finished, we're gonna end up at a termination sequence, and it's gonna stop, and this mRNA is gonna be released and allowed to leave the nucleus. But before it does, we need to do a couple of housekeeping items to it. All right, the first one is we have within the RNA something called an intron, okay? And these are non-coding regions. In other words, these do not code for a protein, okay? We used to call them junk back in the day, back when the dinosaurs were and Mrs. Klug was in school. We called them junk DNA because we didn't think they did anything, but they actually do some stuff. But what they don't do is code for a protein. So we got to take those out, and then we're going to then put the exons, which code, these are the coding portions. We're going to put those together. That's called splicing. And then we're going to put on some protection. And our protection is going to look like a hat, a 5' cap, so a cap on the 5' end, and a poly-A tail. And basically, this is to keep, getting in and out of the nucleus is tough business. Hanging out in the cytoplasm with all these different organelles just floating about is treacherous. And so this is just to keep this very small, single-stranded thing intact so that it can go on to the next step. So we are not going to proceed with the next step in this video, but we are going to watch a video about transcription.
Transcription is the first step in the expression of a gene. It is the formation of a specific RNA sequence from a specific DNA sequence. Transcription initiation occurs at a promoter, a region on the DNA, where RNA polymerase binds. RNA polymerase attaches to the promoter and begins to unwind the DNA. At the initiation site, the polymerase begins reading the DNA template strand and building a complementary RNA strand from free nucleoside triphosphates. The RNA strand grows by the addition of these substrate molecules to its 3' end. This is the elongation phase of transcription. Note that the bases in the nucleotides of the RNA strand form pairs with the bases in the DNA strand. Also, note that the RNA nucleotides contain the sugar ribose, which has a 2' hydroxyl group, whereas the DNA nucleotides contain the sugar deoxyribose, which lacks this hydroxyl group. RNA polymerase functions similarly to DNA polymerase. It adds nucleotides to the 3' hydroxyl group of the last nucleotide. The DNA double helix rewinds as the RNA polymerase moves through. Like the unwinding, the rewinding is an energy-requiring process that is accomplished by RNA polymerase. When RNA polymerase reaches the termination site, the RNA transcript is released from the template. The DNA rewinds completely and the RNA polymerase dissociates from it. The DNA and RNA polymerase can then participate in other rounds of transcription.